quick hint about this first problem. In this first problem, your job is to establish an inequality. And one of the most dangerous things you can do when trying to establish an inequality is to try working on both sides of that inequality at the same time, particularly if how you work on both sides of that inequality is by applying other inequalities to it. It just ends up, when you apply an inequality, half the time you end up applying it in a direction that goes the wrong way. So my advice on working inequality problems, if you're trying to prove that an inequality holds, is to pick one of the two expressions. So I'm going to pick the one that has more going on here, the one that has some arithmetic, the right-hand side. And so I'm going to try to justify that the right-hand side of this inequality is greater than the left side. Whoops, I'm missing an absolute value symbol here at the end. And so if we sort of read what's here, absolute value of x minus 1 plus absolute value of x plus 1, which I'm also missing a symbol there too. Apologies for this typo. Here we go. So we want to establish that this is greater than the absolute value of x. And the typical flow for how this can work is through a string of either establishing equalities and or establishing inequalities that face the direction that we need them to face. In other words, at every step of the game, we should either be replacing this expression with something to which it is equal, or if we don't want to do that, or if we can't do that, we should be always replacing this expression with something which is less than or equal to it, right? So that we're constantly marching in the same direction down the number line, from the initial expression down to the expression that we want to get to, right? We should never be taking any steps to the right on the number line in this process, because once we've taken even a single step to the right that we don't know how big it is, right, we've lost our moral high ground, basically. We've lost our ability to know how the first quantity compares with the last. So any step that you take along the way should either keep you in the same spot on the number line, give me an equivalent expression, or it should take a step toward the left on the number line. Give me an expression which we know is no further to the right than this one, so that by the time we get to the end, we know that this is definitely to the left on the number line from the place where we started. First of all, about question 1. Our philosophy here is we're trying to establish that this inequality holds for any real number x. And so my advice to you was to treat this as a problem where what we're doing is starting with one of the two quantities, one of the two expressions, and working our way towards the other. And in every step that we take should be a step that takes us no further to the right on the number line, right? Because we're trying to show ultimately this is greater than absolute value of x. So we actually need to show that not only is absolute value of x no further to the right, we actually need to show that it's actually to the left on the number line compared to this. So what I saw, I think every group had come to this conclusion as I was walking around, so this part I will give away, that what you ended up doing was using the regular triangle inequality, but using it in the reverse way to the way that we usually use it. So the regular triangle inequality says that the absolute value of a sum is less than or equal to the sum of the absolute values, right? That's the ordinary triangle inequality. That's the way that we usually write it. But that's the same thing as saying, just turning this around, that the sum of the absolute values is greater than or equal to the absolute value of the sum. So either of these can be thought of as a way of getting a plus, getting an addition, which is inside the absolute value, to the outside instead. That's the original form. Or we can also use it as a way of getting an addition which is outside the absolute value into the inside. And that's the fashion in which it makes the most use in this proof. Because what I saw a number of your groups doing is saying, well, if we could just get this plus to be inside the absolute value with both of these quantities, then this minus 1 and this plus 1 would add together and cancel out, and we would have a really simple expression to work with. So that's why this is the right tool for the job in this proof, is that treating the role of A as x minus 1 and the role of B as x plus 1, then applying the second form of the triangle inequality, we can substantiate why this sum of absolute values is greater than or equal to the absolute value of the sum. So we get this plus sign inside of our absolute value with the x minus 1 and the x plus 1. And that's the secret sauce here, because now the minus 1 and the plus 1 cancel. And so what we've done, sort of in a picture here, is we've taken one step to the left on the number line. Well, we don't know that it's a step to the left. It could be a step to the left, or it could be a step which keeps us right in place, right? But we know that we're no further to the right than we used to be by writing absolute value of x minus 1 plus x plus 1, getting that plus sign inside the absolute values. But when you simplify that, what do you end up with? Yeah, inside the absolute value, you just get 2x. And because of the multiplicative property of absolute value, what's another way to write the absolute value of 2x? Absolute value of 2 times the absolute value of x. And what's the absolute value of 2? 2. So what we end up with here is we've ended up able to show that twice the absolute value of x is no further to the right on the number line than the quantity that we started with. It might be to the left, it might be in the same spot, but it's no further to the right. So I'll just write the 2 absolute value of x underneath here. 2 absolute value of x. And so the last question then is, why do we know that 2 absolute value of x is greater than absolute value of x? Why is that true? Because 2 is greater than 1, first of all, right? So this 2 is greater than 1, absolute value of x. And also, that was one of our order axioms for the real numbers. So reaching back into 1x in our course, one of our order axioms is that if a is greater than b, and if c is greater than 0, then CA is greater than CB. Actually, it's an if and only if. Sort of write it like that, right? Because we could trade multiplication for division instead. And so, because 2 is greater than 1, and because the absolute value of x is positive, or non-negative, I should say, right, then that means that 2 absolute value of x is greater than 1 absolute value of x. And so, again, conceptually, our first step took us either to the left on the number line, or at least it didn't take us any further to the right. So it was definitely not a step to the right when we replaced this purple quantity with 2 absolute value of x. But our second step here is definitely a step to the left, because 2 is strictly greater than 1. Okay? It's not just greater than or equal to, it's strictly greater than. And so reading this whole thing from beginning to end, we know that in total we must have taken an actual step to the left. And so the purple quantity must be greater than the red quantity, which is what we were trying to prove.